All right, welcome to your first pre-lecture for ENVE 210. So we're going to start by going over units, unit conversions, which we also call dimensional analysis, and a concept which we call dimensional homogeneity. And what this is meant to do is this is meant to help you review unit conversions, review a lot of the concepts we're going to use through the class. And the idea behind dimensional homogeneity is that it's going to help you figure out what you do and don't know from a specific problem. So let's get started here. So when we talk about units and dimensions, we tend to use those two words interchangeably, but they actually mean different things. So whenever we have a measured or counted quantity, it's going to have what we call a numerical value, which is something like 3.56, and a unit. So the unit is whatever there are 3.56 of. So it could be meters, could be feet, could be seconds, all sorts of things. I'm sure you've seen units before, but just clarifying this definition. A dimension is a property that can be measured or calculated by multiplying or dividing other dimensions. So slightly different conceptually, but a lot of times they get used interchangeably when it comes to analysis. So for example, when we have things that are measured, we can measure length, time, mass, temperature. We have devices to do all of those things, but we can also calculate a lot of different parameters as well. So these would be different dimensions that we can calculate. So for example, velocity being length divided by time, volume being a length cubed, and density being a mass divided by a length cubed. So you can always have a measured quantity. There are actually very few things that we can measure in terms of quantities. And then you can have calculated, and there's quite a few calculated dimensions that you can actually have. So keep that in mind that there is a slight difference. There's always a numerical value and there's always a unit. And on our assignments in this class, we always want to have units associated with our answers. So units are like algebraic variables when they are added, subtracted, multiplied, or divide. So it's important to note that two quantities can be added or subtracted only if the units are the same. So for example, if you are subtracting 1 centimeter from 3 centimeters, you get 2 centimeters. So if you were to replace each of the units with x as a variable, it would read something like 3x minus x is equal to 2x. And so whenever you're adding or subtracting, the units must be the same, and that's important. You can always combine numerical values and units by using multiplication and division, and you will get new units. So this is important because addition and subtraction of units is different from multiplication and division. So for example, you could multiply 3 newtons times 4 meters to get 12 newton meters. And that's a new unit that's combined by doing the multiplication or the division. So as another example, we could have 5 kilometers per 2 hours, which gives us 2.5 kilometers per hour. So you can combine units in many different ways. With addition and subtraction, you want to make sure everything has the same units. When you do multiplication and division, everything is going to get combined into new units. And that's going to play into this concept of dimensional homogeneity in a moment here. We do conversion of units. Sometimes we hear it called conversion, but sometimes it's also called dimensional analysis. So if you open up a textbook, many times dimensional analysis is the term that's used. So when we convert things, we use what are called conversion factors. So they are ratios, basically, of one unit to another. So x of blank unit and y of blank unit. When you divide the two in a ratio, that is a conversion factor. So they're used to convert one unit to another set of units, and you can use multiple different conversions to do the dimensional analysis. So as the example on the screen shows, you can take 36 milligrams, use the conversion factor of 1 gram is equivalent to 1,000 milligrams, and you can find that there's 0.036 grams of that sample. So that's a very simple dimensional analysis we can perform. So it's going to be important in this class as a way to help you check your work and as a way to make sure your answers are correct, that you carry your units along with your calculations to avoid making mistakes. It's important to save you from common errors, and it also helps you gain a little bit more understanding of your mathematical equations, and that's important as well. When we have all of those conversion factors together when we're doing dimensional analysis, we call that a dimensional equation. That's a series of conversion factors used to convert from one section to another, from one unit to another. And it has the general form that's shown on this slide, where we have the quantity in units times a conversion factor times a conversion factor, on and on and on, as many as you need in order to get to the final answer. So we're going to have an example on this slide, and whenever we have examples in pre-lecture, my recommendation to you is that you take a pause and you try the example yourself. If you simply listen to me explain the lecture, a lot of times the learning on your own personal learning is not going to be as deep or as important and impactful for you. So I do recommend taking that pause. So we have an example here where we want to convert an acceleration from 1 centimeter per second squared to 1 kilometer per year squared. And this is a really great place to just pause and see if you understand what's going on. And then I will show you the solution. So if you want to take that pause, I recommend doing it now. Hopefully you took that slight pause so that you could try this yourself. And here's the dimensional equation associated with acceleration to convert it from 1 centimeter per second squared to 1 kilometer per year squared. And whenever there are multiple equations on the slides in your pre-lectures, please feel free to pause the video at any point to make sure that you are writing things down. I may go slightly faster than you can write, so please do make sure that you take that second to pause. So there's your answer. Double check, pause the video so that you can make sure that you understand how that example works. All right, we are going to have some common conversions throughout class, and one thing that we're going to need to do quite often is go between mass and moles in this class. So that's going to harken back to when you took chemistry previous to this class. So what we want to do is we want to know what value do we use to relate mass to moles. And the answer to that is the molecular weight. So remember that your molecular weight is found by looking at the periodic table, and your molecular weight is in units of grams per mole or kilograms per kilomole. So that's important to note. So that's not on this slide. So again, if you need to pause and make sure that you write down those units, that's important. When you convert from mass to moles, you want to look at your units. So remember, your molecular weight is grams per mole. So if you multiply that by a number of moles, you'll get a mass. If you take a mass and divide it by the molecular weight, you will end up with something in terms of moles. So this is simple dimensional analysis that starts to turn itself into a formula that we can use. But you never have to remember the formula if you don't want to, because it's simply a conversion factor. So this is one that you're going to see over and over throughout the class, where we take the molecular weight and use it as a conversion factor. So one of the other things that we have to consider is systems of units. So we're going to see many different units in this class. And when we talk about units, we have a couple different ways of talking about them. The first is what we call a base unit. So this is something like mass, time, length, temperature, electrical current, light intensity. Those are some of the 6 basic units that you would see. And then we can have what are called multiple units, and these are defined as multiples or fraction of the base units. So things like minutes or hours are multiples of seconds in time. So those are different multiples of that base unit. Then we can also have what are called derived units. And derived units can be compounds, so they can be found by multiplying or dividing multiple units. For example, centimeters cubed, feet per minute. Or we could also have derived units that are defined as equivalents of compound units. So for example, 1 Pascal is equal to a certain amount of atmospheres is equal to a certain number of newtons per meter squared. So you can have things that are defined as equivalents and things that are found by multiplying and dividing units. So for an example, 1 Newton is the same as 1 kilogram times a meter per second squared, because we know that force is defined as mass times acceleration. So that's what you're seeing here. A mass in terms of kilograms times an acceleration in terms of mass per second squared, and that is equivalent to what we call 1 Newton. When we talk about units and unit systems, we are primarily going to work with the SI unit system, which is the same as the metric in this particular class. So we have 6 different quantities. We have length, mass, moles, time, temperature, electrical current, and light intensity. So I guess 7 if we count that correctly. And you're going to see the base unit here. So meters, kilograms, gram moles, seconds, kelvins, amperes, and candelas. And you'll see the symbols for those. For the purposes of this class, anything that is highlighted in red is something that you may see. We will not talk about electrical current or light intensity in this particular class. You can also have derived units in the SI system, and some of the derived units that we're going to care about are things like volume, force, pressure, energy or work, and power. So units of liters are units of volume. We have Newton for force, Pascal for pressure, joules for energy and work, and watts for power. So a lot of these we're going to see when we get into energy balances. Volume we're going to see quite often when we talk about mass balances. The last concept that I want to talk about is dimensional homogeneity. And so basically what this is it means that all terms that you add together on both sides of the equation must have the same units as each other in order to be added up in a system. So whenever you have an equation, something like x plus y equals z, the units of x and the unit of y must be the same. And we can use what we know about multiplying and adding and subtracting units in order to figure out the units of an unknown quantity. And that's all that dimensional homogeneity really kind of is useful for in this purposes of this class. So if you break down those words, dimensional is related to units, homo means the same, and geneity is an origin, so it has the same origin or the same units. So that's what's going on. So as an example, we can consider the equation on the screen. We can say D is in terms of feet, 3 is a number, T is in terms of seconds, and 4 is a number itself. So if that equation is valid, we want to know what are the dimensions of the constant 3 and 4. And if the equation is consistent in its units, what are the units that we have? So this is an example of something that we might need to do in class to figure out what's going on in a system in terms of units. So if you take a look at the solution here, and again, maybe try this yourself first, but if you take a look at the solution, in order to be valid, you have to be dimensionally homogeneous. So if you look at D is in terms of feet, just feet. So that what that means is that if 3 is multiplied by time, and time is in terms of seconds, then you have to have 3 have units of length per time, because length per time times time gives you a length, which is what is equal to D. And that also means that 4 needs to have units of length as well in order to be able to add it to 3t. So each unit for each system or each set of variables on one side of equation, if you're adding or subtracting, need to have the same units so that they can be added and subtracted, but they also need to be the same unit as what's on the other side of the equal sign. And that's all that dimensional homogeneity really means. So let's do one more example of this. And again, I recommend pausing it, trying it for yourself, and then seeing if it makes sense to you. So, for example, if we do a little bit of some SDG work, if we have target 12.2.1, it's going to measure material footprint in order to help quantify sustainable management and efficient use of natural resources. So a non-governmental organization or an NGO has recorded their information for target 12.2.1 in units of material footprint per gross domestic product, which is also known as GDP. However, when they're reporting their values to the UN, the United Nations, the UN requested the number in material foot per capita. So we want to know, how can the NGO use one conversion value to change what number that they have and the units they have to the units that the UN is requesting. So how do we change from material footprint per GDP to material footprint per capita? What would be the units of the conversion factor? So again, take a pause and see if you can solve this by yourself. The solution to that problem is that if we want things in terms of material footprint per capita, but we have material footprint per GDP, that means we need to multiply the number that we currently have by GDP per capita in order to get the number that the UN is interested in. So this is a type of unit analysis that you can perform to make sure that you understand what types of numbers and what types of units need to be associated with each thing in an equation. It's a really great way to check your answers as we go throughout the semester and as we move through different types of problems and as they get more complicated. So that's going to close us out for this lecture on units, unit conversions, and dimensional homogeneity. Make sure that you've taken notes on all of these slides, and then on Canvas there is something that you need to submit for the pre-lecture. So make sure that when you look through these slides you understand the content, because there will be some small questions on Canvas related to these slides. I'll see you in class and we'll go through some exercises specifically related to unit conversions and dimensional homogeneity.